Assalamu alaikum warahmatullahi wabarakatuh. Today is our first presentation on analysis of frames, part 1. So what is special about frames? Frames, they have bending moments and shear forces like beams. And a frame also has normal or axial forces like trusses. So it has features from both. And to analyze frames, we need to draw diagrams for bending moments, shear forces, and normal forces. So now there is a new element, the normal force, different than the beam. Normal forces are parallel to the member or normal to its cross section. This is why they are also called axial forces. While shear forces are perpendicular to the member or parallel to its cross section. Rigid connections transfer bending moments from one joint to another, so from one member to the other. So the summation of moments at a joint should cancel out. This is a general rule you need to understand. So for example, this is a very simple one member problem. You have a member that is at an angle, and this member it has a 40 kips force at its middle, vertical. So if we analyze this force, we will find that when dealing with a frame, you always need to analyze a force parallel to the member and a force perpendicular to the member. So because the 40 is not neither parallel nor perpendicular, you need to analyze the 40, cosine the angle and sine of the angle. So this angle is actually, the tan of the angle is 3/4. The tan of the angle is the horizontal, is 3/4. So this is the very famous 3-4-5 triangle that we have dealt with several times. So 40, the component of the 40 that is parallel is the 24. The component parallel to the member is the 24. The component perpendicular to the member is the 32. Same thing for the reactions. We have two reactions, 20 kilonewton, 20 kips and 20 kips up. So when you analyze them, when you resolve them, you will find 12 kips axial in the axial direction and 16 kips perpendicular to the member. So based on that, if we take a cut just after joint A, we will find a shear force of 16 kips, which is in the same direction of that arrow. So this is a positive shear, 16 kips in that same direction. Then it's constant until we reach the 32. If I take a cut just after the 32, so now we'll find 16 minus 32, this is minus 16 kips. So this is our new shear force, and it remains the same until this other 16 kips comes again, and it will close it to be 0. Again, the shear force diagram must close to 0 at its end. This is the same thing like what we have seen with beams. When dealing with bending moment, very similar to the beams, the maximum moment is at the location of zero shear, which is here, as you could see. So again, if you want to know how did this 160 come, simply take a moment here, take a moment here at this point. So from this side it is 16 times 10. From that side it is 16 times 10. So this is 160 kip feet. Or calculate the area of that rectangle, 16 times 10 again. So this is the 160 kip feet. However, for the axial force, it is the reverse of the shear force, or the reciprocal of the shear force. In terms, now I'm not looking perpendicular to the member, I am looking in the direction of the member. So if I take a cut just after A, any point between A and the concentrated load here, I will see a minus 12 kips force, which means it's a compression. So if I take a cut here, the member wants to compress by 12 kips, which makes sense. Then the 24 comes opposite to the 12. So now if I take a cut just after this point, I will see a tension force because it is 24 minus 12. So now it is positive 12. Okay, and again here the reaction will get it back to 0. So this is the very basic concept when dealing with frames, is that you must look at things from the local coordinate perspective. بمعنى لازم احلل الفورس بتاعتي يا اما عموديه يا اما موازيه للممبر. الاتجاه الموازي للممبر يديني الاكسيال فورس، الاتجاه العمودي على الممبر يديني الشير فورس. Let's take a more complicated example. Here we have 3 members making out a frame. So first we get the reactions. So when calculating the reactions, sigma m a equals 0, 6 times 4 times 2 plus 16 times 5 times 2.5 plus 12 times 5 plus 16 times 4 minus 8 Vd. So that gives us that Vd is equal to 46.5 kN. Sigma Fy equal 46.5 plus Va minus 12 minus 16.5. That will give us that Va is equal to 57.5 kN. Both are up. Then sigma Fx equals 0, 16 plus Hd plus 6 times 4. So that gives us that Hd is equal to 40 kN to the left direction, from right to left. So if we break down the forces, look at each member on its own. If we look to member AB, we will see that again, if I take a section just beneath B and look down, I will find a 57.5 kN force coming up, and I will find the 6 kN times the distance, which is 4. If I take a section and if I take moment at B, I will see 6 times 4 times 2, which will give me 48 kilonewton meter. And if I take a joint here and I look at the forces from that side, I must find that this moment is exactly equal to that moment. The 48 is counterattacked by the same 48. So again, I must see joint equilibrium here. However, if I look at joint C, if I take a section at C and I want to look at the axial force, I should be very aware how will I calculate the axial force. So the axial force in such a thing at joint C, it is 61.2 just beneath C. Just any point between C and D. Where does it come from? It comes from the component from 40 kilonewton and another component from 46.5 kilonewton. Okay? So if this angle is alpha, that means that I need to get the 40 kilonewton cosine alpha. This will give me what? This will give me the parallel to the member component. And the 46.5 will be multiplied by sine alpha. This will give us the direction here, axial to the member. These together will be minus 40 sine alpha, minus 40 cosine alpha, minus 46.5 cosine alpha. Both will give us what? As negative 61.2 kilonewton in compression. And again, when you write this, you should either write compression or write minus 61.2. You should clarify. For member AB, it's very easy, by the way. For member AB, it's simply the reaction. So if you take a cut anywhere between A and B, you'll find 57.5 kilonewtons in compression. Okay. If you take a cut between B and C, what will you see? You will simply see what? You will simply see this force. The 6 times the 24, which is, sorry, the 6 times 4, which is at 24 kilonewton. So if you take a cut between B and C anywhere and look at the axial direction, you will see 6 times 4, which is 24. So again, this is negative 24 kilonewton or 24 kilonewton in compression. Now let's look at the shear force. The shear force is now perpendicular to the plane. It's not parallel to the axis. It is perpendicular to the member. It's perpendicular to the member. So if I take a section at A, that's a roller. I don't have any force at A. Exactly at A, there is nothing. So it's 0. So if I take a section just below BC, I'll see what? I'll see the 6 times 4, which is the 24. You'll notice that this 24 is that same 24. Why is that? Because, simply speaking, we have a member that was subject to 24 kilonewton and transferred that 24 to the other member as an axial force. Okay, if I look at BC and I take a section just after the 12 kilonewton, what will I see? I will see the VA, the 57.5 kilonewton, minus 12. So this will give us what? 45.5 kilonewton. On the other hand, if I take a section just here, just at C, what will I see? Just before the 12 kilonewton here, what will I see? I will simply see what? I will simply see the same 45.5 minus 16 times 5. So 45.5 minus 80, this is negative 34.5 kilonewton. And again, this 0 shear, this is the location of what? Of my maximum moment, and I will simply get it by similarity of triangles. So what about this member? If you want to deal with this member, look at the shear force here. Very simple. Do exactly the opposite of what you have done here for the compression force. So now I will get the other component, the component of the 46.5 that is perpendicular to the member, and minus the component of the 40 perpendicular to the member, and this is this nice value, which is small. It's 4.1 kilonewton. What about the bending moment? Let's look at the bending moment. Simplest points in the bending moment, point A and point D, they must be 0. That's for sure. We know that because A is a roller, D is a hinge. They must be 0. Okay? If you take a section just beneath B, you will simply see 6 times 4 times 2, which is